And like I said, I think we're ready to go. We are, we got a little bit of material left over from lecture 21. That's where we were talking about mostly security. And we ended with what to me is the most interesting part of that, what technologies can you use to help improve the secrecy or improve authentication within your program. And I know I said this already, so I'll say it real fast. Encryption is one of our most reusable techniques for enhancing the security of our program. Certainly, if you got a buffer overflow, all the encryption in the world is probably not going to matter. But if you're worried about an attacker compromising the system you've put together, this is a way of making sure that they can't do anything, or trying to make sure that they can't do anything bad, even if they gain illegitimate access to your system. We talked about this last time. We're kind of, you'll get to see this again in operating systems class and probably in a few other classes in addition to that one. But this is kind of our first taste of encryption for many students. We described last time the idea of symmetric encryption, kind of the simplest way of trying to do encryption. You take a message that we called plain text, you run it through a process called encryption that, under the control of a key that the user will keep secret, it turns it into what looks like random garbage. It turns it into what looks like random bits that we'll call ciphertext. That part's easy. I can turn human readable text into random garbage, but this needs to be a reversible process. So for symmetric encryption, to reverse the encryption, you need to have access to the same key. And then a decryption process can get you back your plain text from the ciphertext, provided you have the right key. And there are, and this is kind of where we ended last time, there are a number of techniques for doing symmetric encryption. DES, that's short for Data Encryption Standard, is one of the early ones, and it's probably been around and is still in some form used today. It is a way of encoding a message by breaking it up into fixed size blocks. So it's what we would call a block cipher. It works by encrypting the message a block at a time and encrypting it under the control of a 56-bit key. And that 56-bit key is aligned with the block size. So the block is 64 bits or 128 bits. So that's 8 or 16 bytes. And that lines up well with a key that's 56 bits in length with an extra bit for every byte. That's kind of the weak, by today's standards, that's kind of the weakness of plain old DES, is that key is kind of small. And a brute force guessing attack might be able to guess your key, even if you tried to be clever when you came up with it. So more modern encryption techniques use a larger key space, among other things, like triple DES or AES that I've listed at the bottom. We can play with this stuff on the common platform, or if you've got a Linux machine, you can do this yourself. There's a tool, OpenSSL. It's part of the set of software that's used for an SSH login or for SFTP connections. And it knows a bunch of encryption algorithms. And if you ask it, like I'm doing here in this example, it'll list the different encryption algorithms it knows how to do. And you can see right here is the one we were just talking about, DES. It has an implementation of that. And I thought we'd give it a try ourselves. So here in this shell window, I've got a login to a common platform machine. I just remotely logged into it from my terminal window. I've got one source file that we may play with later. But that program that we just talked about, OpenSSL, is already installed on this machine. And we can try using it to do encryption. And I'm kind of following along with the slides here. So if you want to follow along, you can see the commands I'm typing. And then once I'm done, I'll go back and I'll try to fast forward through that in the slides. So that OpenSSL command can do encryption using those different algorithms it supports. We just need to come up with something for it to encrypt. So I'm going to make a message. I'll just bring up a text editor, VI. I've used this before this semester. And let's make a file called message.text. And this is a test. So that'll be what we put in our message file. So I've written it. If you want to take a look at it, you've probably used cat is a handy way to just see what's in a file without having to bring it up in an editor. So if we cat message.text on the terminal, it shows us the text we just put in there. So that's our message. If we want to encrypt this using DES, using the OpenSSL tool, OpenSSL, so the same command we just talked about, we need to tell it what to do. So I want you to encrypt using DES. So it knew a bunch of encryption algorithms, both symmetric and asymmetric. This is the one we want to use. And then we just have to tell it what to read from and write to. So as the input, let's have it read message.text. As output, let's have it write out message.bin. And I'm putting the .bin at the end because the output's going to be binary. It's not going to be a text file. It'll look like random garbage. So when I hit enter, it'll encrypt it using DES. But like I said, DES does its encryption under the control of a key. And I've got to provide the key. So I'll just type in ABC 123, not a very good key, ABC 123. It makes me type in the password twice. And this is typical. It wouldn't really have to do that, but this is just to guard against human error. If I have a typo in typing in my password and it encrypts and I didn't use the password I thought I did, then I may not be able to get my message back. So it makes me enter it twice just to help make sure I don't make a mistake in my password. And now if we take a look, well, there's the encrypted message. I've still got my original file there. And if we look at that, it's still got my original message. But if OpenSSL encrypted this correctly, I shouldn't need that unencrypted message anymore. It ought to be captured in the encrypted one. So let's remove the original with the idea that I can get it back as long as I remember my password. And if we take a look, you can see there's my encrypted message. I didn't check, but you can see, well, if we had checked, it got a little bit bigger under encryption. That's typical, especially if you're using something like a block cipher. We mentioned that earlier. A block cipher breaks the image into these fixed size blocks and then encrypts each one. What if the message isn't a multiple of the block size? Well, normally the last block might be partly full. So it fills the rest of the last block by padding it with typically zeros or something like that. And that's going to make, for many messages, that's going to make them a little bit bigger under encryption. So I didn't check before I removed it, but my original message wasn't 40 bytes in size, but the encrypted one is. I deleted my original message. I hope I can get it back. All I have to do is tell DES to decrypt. I have to tell OpenSSL to decrypt using DES. So OpenSSL, same command. I give it similar options. ENC says I want you to do encryption. It can do a variety of things. Even though we're decrypting, I want you to do an encryption task. We're going to decrypt with DES, and this option, the -D, says to decrypt. So I want you to undo what I did when I encrypted this with DES. And then for the input file, I want you to read message.bin, and for the output file, I want you to create a new file. Let's call it the same thing, message.text, same thing we started with. When I hit enter, I still have to type in the password. It didn't remember the password. It certainly didn't put it in the encrypted file. That'd be useless. It's depending on me to enter the password. So I just have to type in ABC 123. And then, well, I did get a message.text. So it created that file. Let's see if it contains the right thing. Message.txt. Yeah, sure enough, I got back my original file. I guess we didn't do this, but I wonder what the encrypted file looks like. Let's bring it up in our editor, message.bin. So this is what we had temporarily. And you can see, well, it's got a little bit of human readable text. But the rest of this out here is what looks like binary garbage. It is the encrypted version of my file. And if I'd provided a different key, even if I started with the same file, if I'd provided a different key, it would have looked like different random garbage out here. So that's kind of what I want. If encryption is doing its job, my encrypted file shouldn't look kind of like my message. It should look completely different. It should look like random garbage. And that's what I've got here. Questions before we go back to the slides? All right, so here's what we just did. So we described what symmetric encryption was. We talked about OpenSSL, and we ran this command to get OpenSSL to do encryption with us, or sorry, for us. And then we deleted our message and got OpenSSL to do decryption. I guess one disadvantage of how OpenSSL does this is we always have to type in our password. In fact, when we encrypted, we typed it in twice, just to make sure. We had to type it in twice to make sure it matched. We don't absolutely have to do that. If you wanted to automate encrypting stuff, say if you wanted to use it in a script or under the control of a different program, there is a command line option that lets you specify the password. And that's what I put in red here, -pass, and then it's pass : and then the text of the password you wanted. So if I wanted to automate encrypting and decrypting, then I could put the password on the command line. But like the slide says, that'll work, but it's really a terrible idea. And if you look at the documentation, and I put that a couple of places on my slide, and if you look at the documentation for this command, it'll tell you about this option, but it'll tell you probably shouldn't use it. And the reason is, well, this, ps-ef. It's not the only reason, but this is an example. The PS command lists running programs. It lists processes on the system. And it doesn't just list your processes. It can look at all the processes that have been run on the system, including their command line options, including ones that are run by different users. On a Unix machine, the currently running programs, that's public knowledge. Anyone can see that, including anything that was put on the command line option. And you can see here, well, I mean, here's a list of a couple of copies of me and other users that are logged into this system right now, along with the commands they're running and the options to those commands, which means if I did this, if I ran OpenSSL and I put my password right on the command line while that command is running, now someone who is in the same room with me who could look over my shoulder, they might see this on the terminal, and that's bad. But someone who's logged into the same system, even if they're in another part of the world and they're looking at what's happening on the system, they could also see my password. So this is a bad way to automate using SSH. If we wanted to write a program that could use, or a C program that could use encryption, well, here's how we could do it. We learned about the system command earlier. That can run anything that you could type at the shell. Well, so you could run OpenSSL via the system command, and you could provide the password right there on the command line. But this is a bad idea for two reasons. One of them, the reason we've been talking about, it's not going to be very secure for anyone else on the system could see your password when you did this, and it's probably going to be slow. If you're starting from a C program, why would you want to go through the shell to run another program that itself might have been a C program to do something that you could just do yourself? So for doing encryption, rather than running a separate command, it's probably a better idea to use a library for this. And there are a number of libraries available to the C programmer. Same thing if you're in Java. In the Java API, there are standard libraries for doing encryption. Since we're doing C in this class, one way we could do this is to include the DES crypt header, and that's what I've listed here. This gives you access to a few functions that encrypt and decrypt using the same symmetric crypto system we just talked about, using DES. Encryption and decryption can be used on any type of data, so they take their input as an array of bytes. They don't even care about whether it's a string or not. For encryption and decryption, think of that as working on any type of data, so any sequence of bytes. ECB crypt is how you can encrypt a block of data using a key, using the DES standard. Let me talk you through the parameters real quickly. First, there is the data you want to encrypt. So a pointer to the start of a block of data passed in as a char pointer. It's not a string, so it's not necessarily going to be null terminated. In fact, it might have zeros inside the block of data. So we got to say how long the block is, since we can't depend on null terminators to mark the end. So that's the next parameter. The length parameter says how big the data is, how many bytes of memory it is. The third parameter is, do you want this same call can encrypt or decrypt? And there's a constant. You get it from this header that says which one you want to do. So DES encrypt will encrypt the block. Decrypt will decrypt it. And when I say it encrypts or decrypts the block, it goes in and changes what's inside the block. It messes with the bytes inside this block, encrypting it via this key. So the key is an 8-byte key, and you just pass in a pointer to the first of those bytes. So think of this first one as an array of 8 bytes containing your key. The next one is an array of however many bytes you've got that you want to encrypt. This is how big it is. And this last one is whether you want to encrypt or decrypt. Because this is a block cipher, it's depending upon your block of data being some multiple of 8 in size. If it's not, if you got a block of data that's 15 bytes long, then you're going to have to pad that data. That normally means adding an extra byte to the end to get it up to adding extra bytes to the end to get it up to a multiple of 8. The reason I said an extra byte a moment ago is because of the example I picked. If it was 15 bytes of data, you're going to add one more byte so that it's 16 bytes instead. So it's a multiple of 8. So this function lets you encrypt and decrypt. This function prepares your key. Your key can be any sequence of 8 characters given by the user, but the DES code has to do some preparation work for the key. And this function does it for you. So before you can actually use your key, you have to call DES set parity on it. And you pass it in your key, and it goes in and essentially turns on extra bits within the content of that key, so it satisfies some constraints before it does the encryption. These 2 calls are enough to let us do encryption. If and this is some sample code. This is posted with today's lecture, and you get to do this as part of, I think it's exercise 21. You get to write a little bit of code that does I don't remember if it's encryption or decryption, but it uses this API to do one of those 2 operations. So this is just showing off how you could do this or what the calls look like. I include the header file we just talked about. I made up a key. It has to be 8 bytes in length. So I had to make up ABCD. Well, I did make up ABCD 1, 2, 3, 4. I can't use that directly. I have to run that through DES set parity. So that's what I do next. Then I made a message I picked a message that's 24 bytes in length. So that's a multiple of 8. If it wasn't, I would have to pad it with something to make it the right length for this algorithm to work. And then I run descrypt on that, and that modifies this array. It goes in and messes with what's in this message array, making it look like random garbage. In this code, I don't print it out after that, but I could. It wouldn't look like characters anymore. It would look like random garbage. Before I do anything else, I turn right around and decrypt it. And then after I've done this, my array message using the same key to decrypt should give me back what I started with. I should get back my original message. Questions? I just saw something on the chat. All right. What does it take to build a program with this? Well, just like the math stuff is in its own library, the DES encryption stuff is in its own library. It's a library called libcrypt. So if you want to use that, you need to include that header, but you also need to link with the library. So you'll need -lcrypt when you build your executable. Like I said, you get to do this in exercise 21. And then when you build that program, you'll need to make sure you link with this library. And probably if you were doing some exercises on a Macintosh or something like that, this one you may have to do on a common platform machine. So we've been talking about security, and we spent a little bit of time talking about encryption as a really useful tool for enhancing security. In general, security is a good thing to think about up front in designing an application. Imagining that you can build an application and then add on security features at the end is usually a bad idea, and usually that results in an application that has a lot of vulnerabilities. Planning ahead, and especially planning for building in things like encryption where it's needed, is a much better way to go. We mentioned at the very early in this lecture, we mentioned some reasons security flaws end up in programs. And you've got to program defensively to try to avoid those. That includes things like making sure that you don't leave in buffer overflow vulnerabilities, that you don't depend on the user to type valid inputs. You got to plan for a user that's trying to break your program, even if you don't think very many users will really try to break your program. You have to think maliciously. If you want to guard against security vulnerabilities, you kind of have to imagine someone's trying to break your code. If you're using encryption, and if you're trying to validate what the user is doing, you often have to worry about validating the user, making sure the user is who they said they are, making sure that you have an authentic user. And and I'm kind of building up to this next slide where I say, well, one of our standard ways of authenticating users is making sure they know some secret information, making sure they know a password. And that's what this little pretend piece of code does. I've got an array where I'm going to store a password. I prompt the user for a password. I read in a password. I'm careful to make sure I don't buffer overflow when I do that. And then I check the password to make sure they typed in the password they were supposed to. And then if they do, maybe I'll let them do the operation they're trying to do. If not, maybe I'll give them an angry message and tell them that I'm not going to do what they asked for. This is a terrible way to implement a password in your program. And the part at the bottom shows the reason why. You don't want to hard code a password in your source code. Like here, the password is Albuquerque. That's a bad thing to put in your source code, because any user who came along and could see your source code, they'd see the password right there. In fact, it's worse than that. If they can look at your executable, then that password must be buried somewhere inside your executable. And there are system utilities that'll extract it for you automatically. And that's what I'm showing at the bottom. There's a strings command that'll extract all the strings stored in an executable. And for this little program fragment, you can see it's getting all of the strings, including the text of that password I had up there. Trying to hard code a password in an application here, kind of imagining that, well, as long as they can't see the source code, then they're not going to be able to know the password. Well, that's wrong. And I would say that's in that category of either not understanding the execution environment your programs are running in, or not adequately protecting secret information. That if Albuquerque is a password, then that needs to not be written out in plain text in source code. And it also needs to not be available by looking at my executable. How do you store a password? Normally, we don't store that in a program. We count on storing that in a file. That makes it more configurable, and it lets us protect access to that password. In fact, in a lot of cases, we might need to generate passwords that no human ever came up with, that are just generated by machine. And then we can either use that machine generated password or replace it later with a human generated one when we need to. And that's what this piece of code at the bottom is showing. If you had to generate a randomly generated password, maybe a throwaway password that you're going to replace later, or that one that no human could guess, you could do it with code like I'm showing at the bottom of the slide here. But that would be a terrible idea. And that's kind of the point of this. What does it take to generate a random password? Well, what I'm showing here is a bad way of doing it. Let me tell you what I'm trying to do here, and then we'll quickly say why it's bad. I got room for a 14-character password. I'm going to loop through those 14 characters. For each character, I'm going to pick a random letter. So I'll take A plus, rand modded by 26 should give me a random number between 0 and 25. So that'll give me a random lowercase letter. I stick 14 of those in the password, and then I put a null terminator at the end. And I've got a password that looks kind of random, but you'll remember rand is a pseudo random number generator, and it's not automatically seeded in C, which means if I ran this program twice or 100 times, it would give me the same random looking password every time. So it's not really very random. Anyone who had access to this code could easily figure out what password it generates. We already figured out a way to improve this. We said, well, since the random number generator doesn't automatically seed itself, or it starts with the same seed every time, we could seed it ourselves. We said a couple of lectures ago, if we just took the time of day, measured as, remember time, this is that function that returns the number of seconds that have elapsed since January 1st, 1970. If we use that to seed the random number generator, then we will get a different password every time we run this program, as long as you don't run it twice in 1 second. So that would make the password harder to guess, but not a whole lot harder to guess. If an attacker knew that you were generating a password using code like this, and they knew about when you generated the password, like even if they knew, well, they generated a password during this week or during this month, it wouldn't be too hard for them to try every possible seed that you could have gotten. It'd be a few thousand seeds they'd have to worry about, but that's no big deal computationally. They could easily try all possible passwords you could have gotten. So this, again, is not a very good source of randomness. What does it take to get a good computational source of randomness? Fortunately, we've already thought of this. On a modern computer system, it's common to have access to a source of randomness. And on a Unix machine, you can read random bits from this source of randomness, and they're they're for things like what we were just looking at. They're for cryptographic techniques. They're for seeding random number generation where you want random numbers that no human could guess. On a Unix machine, on a Linux machine, there's a device called /dev/random. That's what I've got right here. And if you read from it like it was a file, you will get byte after byte of random bytes, where those random bytes are fed by environmental noise. What does that mean? Well, as the computer system is running, it's sensitive to things happening in its environment. It's sensitive to things like packets arriving on the network, or the user typing keys on the keyboard, or moving the mouse. And all of these things have some aspect of noise to them. When the user moves the mouse, there's little bits of jiggling that happen in the mouse that no one else would even know were happening, or no one would know exactly how the user was jiggling that mouse, unless they were right in the same room looking at the mouse. And even then, they probably couldn't tell exactly what pattern of jiggling is showing up on the mouse. Another example might be a packet arriving over the network. When a packet arrives over the network, the computer system knows exactly when it arrived. And someone else, even if they were on the same network, they might not know exactly when that packet arrived on the computer system unless they were running code on that computer system. A Unix machine, a Linux machine collects all of this random environmental noise, and it makes it available for cryptographic purposes in the form of this device. And I can show you how to use this. Normally, you would only need to do this if you were doing some encryption, but this is a way to get access to random bits that you could use to generate something like a random password. So like it just said in the slide, DD is a program for reading and writing sequences of bytes, kind of like copying, but it can read bytes from any device on the computer system. It's got a couple of parameters. You can tell it how many bytes you want to read. So let's try to read 16 bytes. BS equals 1. That's, you can read a block of bytes at a time. So I'm saying what the block size is. I only want to read blocks of 1 byte per block. So these two together say I want you to read 16 blocks, each of them 1 byte in size. And then what do you want to read from? IF equals this thing we were just talking about, dev random. OF equals where do you want to store this? And then this can be any file you want. So let's call it random.bin. All right, and then when I hit enter here, well, DD gives me a report and it says, all right, I've read your 16 bytes you asked for, and they're in the file we just made. If you take a look, sure enough, that's the file we just created, random.bin. If we look at the size, yeah, it's 16 bytes, just like what we asked for. And if we look at what's in it, that'd be a good job for hex dump, because it should look like a bunch of random bytes, so it won't look like text. Let's just print it out as a bunch of hexadecimal values, and then whatever file we just made. And those are the random bytes it just got with the help of the operating system. If you ran this again, let's give that a try. I'll rewind and rerun the same program. And then let's look at what we got this time. We got completely different random bytes. Random bytes that really no other user would be able to predict unless they were running code on the same system we're using. So the intent here is this is a good source for cryptographic applications. Normally when I show this example, I run this a bunch of times. I don't know if I can pull this off today. Normally I run it a bunch of times, and eventually, stall. Every time I'm running DD, I'm getting 16 more random bytes. Yeah, that's what I was looking for. Eventually, you run out of random bytes. What I mean is, well, the operating system is harvesting these from environmental noise, from little things like packets arriving on the network, the user jiggling the mouse, a bunch of different sources. And eventually you can exhaust that supply of random bits. And the operating system has to wait to collect more random bits from things like packets arriving from the network or the user jiggling the mouse. Normally it doesn't take this long, but eventually this will return once the OS has some additional random bits. This is kind of showing, well, what I'm doing works, it's just not what you're supposed to do. Dev random gives you direct access to those environmental or those random bits collected based on environmental noise, but it's an easily exhausted supply of random bits. If you want a set of random bits that isn't as easy to exhaust, there's /dev/ I believe it's urandom. That is a pseudo-random process, kind of like the rand function, but it's fed by the same source of environmental noise. So you're not going to run out of bits if you read from that device. I was kind of being a bad citizen of the computer by reading straight from dev random. I'm a little nervous. There we go. And I ran out of bits, and it took the OS a while to say, all right, I'm going to have to sample some more environmental noise until I can give you the 16 bytes you asked for. That was a long-winded explanation. Gets us caught up with where we're supposed to be at the end of lecture 21. Questions before we move on to where we are supposed to be today, and that's lecture 22. Questions? All right. We are getting near the end of C. In fact, I think we've got today's lecture, and then we've got a lecture on Monday, and then after that, it's going to be all C++. So we just have a few topics in the language that we haven't covered, and I'm going to try to cover as many of those as we can today. The really language features that we've gotten by without so far this semester. And we saved them until today, partly because we didn't really need these until now. But let's see if we can cover these and get caught back up a little bit. And I've listed them here. The first two are the bigger ones, enumerated types and unions, and then a couple of keywords. We'll explain what those mean. Enumerated types. You'll remember this from Java. An enumerated type, just like in Java, C has a way of defining a type that just has a small fixed set of values. Like if you wanted a type with just the values red, green, and blue in it, just those constants as their values. Or if you were writing a program where you had to navigate around a map or a grid and you wanted a type that only had up, down, left, and right as its values. That's what an enumerated type is for. And Java has something similar, and it's for the same kind of thing. It's for having a type that you get to define that just has a few named values in it. Defining a type like that lets you write code that's maybe more readable and where the compiler can catch mistakes if you accidentally try to give a type a value that it can't represent. We've gotten by without this so far, and we've probably, like if we had to pick how to do this before today, we would have done it with help from the preprocessor. We could use the preprocessor to set up values like red, green, and blue, like I'm doing down at the bottom, and we could choose numbers that those each map to. So red could be another name, or could get replaced by 0, and green could get replaced by 1. And then we could just use an integer variable to hold any one of those numbers. And then kind of like the code down at the bottom, we could assign it one of those names. Like if we say color equals blue, we know that the preprocessor is going to replace that blue with the number 2, whatever we picked up here. So we could, within our code, we could use blue as a human readable name for that, for a thing that's going to get mapped to the number 2 when our code gets compiled. And this works fine. Lots of people code things this way. The problem is the compiler doesn't, if you represent enumerated values like this, the compiler doesn't really know what you're trying to do. It doesn't know that red, green, and blue go together, and that color should only have one of these three values. As far as the compiler knows, color's just like any other int. An enumerated type would let us tell the compiler more about what we're trying to do. And maybe with that, the compiler could catch some errors in our code. And just like Java, C supports an enumerated type to let you do this kind of thing. And this is the syntax it takes to define one. It's kind of like the syntax for a struct. So the keyword enum. I think Java uses the same keyword. And then the name of the enumerated type you want to make. So here I made color enum. And then inside curly brackets, a list of all of the values of that enumerated type, separated by commas. And I haven't checked lately, but I think Java syntax for this kind of thing is pretty similar. So here I'm defining an enumerated type that just has values red, green, and blue. Once I've done this, once I've defined an enumerated type like this color enum, I can use it kind of like you would use a struct. If I want to make a variable of this type, I have to use the enum keyword. So I'd have to say, I want to make an enum of that enumerated type. So enum color enum. And then I can declare a variable of that type. And I can give it a value that's any of these four values we said. So we said this enumerated type just has red, green, blue, and orange as its values. So I've got to assign it one of those four values. Notice, just like with structs, I have to use the enum keyword, but, and we'll see this on the next slide, I can use typedef to map that to just a plain old type name. So I don't have to say enum every time I want to use it. Once I've made an enumerated type like this, what can I do with it? Well, mostly just two things. You can assign it a value from the enumerated type. So when you make it, you can set it to red. You can change your mind. Sorry, you can set it to green. You can change your mind later and set it to something else. You can compare values of enumerated types. So my color and your color, this equality test will evaluate true only if they have the same value, only if they're both red or they're both green or something like that. I just said on the previous slide, you can use typedef to come up with just a single type name for an enumerated type. And just like with struct, that's often done. Up at the top, I made a typedef, that up, down, left, right enumerated type to the name direction. And now I can just say direction when I want to make a variable of that type. And that's pretty much all that enumerations do in terms of syntax. They let you use those names up, down, left, right as values for the enumeration, for the enumerated type. You can assign those, in this case, those four values to variables of that enumerated type, and you can compare them. I'm stalling because at the bottom, it kind of shows off what's going on internally. Internally, the compiler is doing the same thing we started with. For an enumerated type, it's storing just a number. And for each of the values you specify, it's thinking of those as an alias for a number. And unless you say otherwise, when you list values in an enumerated type, it's really just using those as aliases for the numbers 0, 1, 2, and so on, depending upon how many enumerated values you give. So an example probably makes this easier to make sense of. For this enumeration, direction is really just another name for an integer value. At least that's how it's implemented. And up is just another name for 0. And down is just another name for 1. And left is another name for 2. And right is another name for 3. And you can see this if you directly access what's in an enumerated variable. Since it's really just since it's represented as an integer, You could print it out as if it was an integer, and it'll show you the numeric value used to store these. So if my direction was right, when you print it out, you'd get a 3. You can even assign back and forth between these. So if you take what's in my direction, even though you said it's this enumerated type, and you assign it to an int, then you'll get its integer value. In fact, you can control the mapping of integers to the enumerated type, and or to the enumerated values, and that's what I'm showing here. Here, I make another enumerated type, but for happy, instead of letting the compiler choose its value, this is the syntax it takes to specify a value. So name of the value, and then equals, and then whatever numeric value you want it to have. So happy is going to be 2 in this case. It would be just another name for 2. If I'd left off this equals 2, it would have started at 0. So unless you say otherwise, enumeration values start at 0, but you can pick other integers if you want. And then they just count up from that integer value. So happy is 2. Afraid, well, you didn't say otherwise, so it's going to be a 3. They count up from the previous value. So again, happy's 2 because you said it should be. Afraid is going to be 3 because it's one more than happy. It's the one that comes after happy. Bored, you said that would be a 0, so that's what it's going to be. Blue for, I guess, sad is going to be 1 because it's one more than bored. Glad is going to be 2 because it's one more than blue. Notice you can have collisions on this. So there's nothing wrong with having 2 values in your enumeration that map to the same integer. It just means if you're looking at that integer, you're not going to be able to tell the difference between them. If you make a value of this type and you set it to happy, since that's represented as 2 and so is glad, then those values are going to be indistinguishable when you look at the enumeration. In fact, you can use other integer operations on an enumeration. It's really just a kind of a thin wrapper around an integer and a bunch of names for values that integer can have. So at the bottom, I'm showing you can make a variable of this type, and you can even add 1 to it, and you can think of that as moving through the enumerated values. So if I set mood to happy and then I increment it, well, I guess now it's going to be afraid. I can even overflow. If I add 1 to it after that, well, now it's going to have a value of 3. Sorry, now it's going to have a value of 4, but that doesn't correspond to any of the names. So after the second increment, mood or my mood isn't going to match any of these values. Questions? All right.
I have a question about the plus, like on the last slide. So if you do like my mood plus plus, that sets it to 4.
Yes.
If you like print out my mood, is it going to print out 4, or is there going to be like an error?
It's going to print out 4. I wish it was an error, because that would make more sense to me. I think this would be more useful if it caught mistakes like that. But C is kind of designed to favor performance over most other things, and having an enumeration really just be another way of having an integer or implemented as integers and mapping names to enumerated values. That's efficient, that's easy to do. So that's what the language does, but it doesn't catch this. When you do the second increment, you're essentially inventing a number that doesn't map to any of these. The compiler and the runtime environment don't catch that.
Okay.
I wish they did, but I guess I can understand why it's done that way. It lets you have a really efficient implementation. Other questions? All right, here I'm showing that the scoping rules for names are the same as any identifier scoping rules. So here I've got a color enumeration that has red, green, blue, and orange in it. And I didn't say otherwise. So red is going to be another name for 0, green's going to be another name for 1, and so on. And then I made a mood enumeration. and I put a bunch of values in it, but it also has blue in it because blue is plausibly a mood you could have. Maybe you're feeling sad. The compiler isn't going to like this because blue is defined in two different scopes. It's part of the color enumeration and mood enumeration, and it has different values in those two enumerations. Up here it would be 2, and down here it would be 3. Even if it had the same value, the compiler still isn't going to like this because it's just like variable declaring. You can have two variables with the same name. You just can't have them with the same name in the same scope. And that's what we're seeing here. The example at the bottom, you can do that because even though blue is defined in color and mood, they're not at the same scope. So if you're inside the inner, or if you're after this line of code, but still inside the second set of curly brackets or this set of curly brackets, then this enumeration has narrower scope. So if you say blue, it's going to think you mean the one in this enumeration. If you're outside this set of curly brackets, it's going to know you must mean this one. So enumerations are kind of handy in C. They're not as well done as they are in Java. Java, through some cleverness, they make it so if you define an enumerated type, you can't really invent additional values in that type that weren't included in the definition. You can't, kind of what we're doing back here where we're inventing new values that don't even show up in the enumeration. Java has a way to keep you from doing that. But in C, enumerations are, they're not as safe to use, and the compiler doesn't catch as many mistakes as it does in Java. But there are a couple of tricks you can do with this. And one of them is, it's a hack, and it's called the enum hack. And I want to sneak up on how you can use it and why it works, and how it does let you get a little additional value out of an enumeration. And so I'm trying to motivate this by the example at the bottom. Let's say I've got a book and it's got a string of up to 99 characters for the title, a string of up to 99 characters for the author. Well, it's unfortunate to have two copies of the same constant there. We might complain that that's a magic number. We've got a way of getting around this, and that is we can use the preprocessor to define a constant. But a disadvantage of using the preprocessor to define a constant is the preprocessor doesn't respect scoping rules. So if I use size as the name of the number of elements in these two arrays, then no one else can use that name, at least not in code that also includes this. So we could have a potential name collision there. And again, because preprocessor symbols, they don't care about scoping the way other identifiers do. But an enumeration does respect some scoping. Enumerations, like we just saw, they can go into or out of scope. So we could use this to define an integer constant that goes out of scope when we don't need it. And this trick is called the enum hack. It is a way of defining an integer constant as part of an enumeration, but not because you really need the enumeration, just because you need an integer constant that's going to go out of scope later, so it won't collide with other names. Enumeration values are considered compile time constants. So that means you can use them in any place where a compile time constant is required. Here, this is just showing you could use them for things other than representing an enumerated type. And that's what I'm showing here. I'm going to make a list. For size, instead of using the preprocessor, I just made up an enumeration. I didn't even give it a name because I'm not really going to use it as a type. I just used it as a holder for the size, the size enumerated value, and I mapped that to 100. So size is going to get replaced by 100, or at least the compiler knows size is a name for 100. but it still considers this a compile time constant. So you could use it, again, wherever a compile time constant is required. And we've seen a few places like that, like the size of a global array, like what I'm doing here, or the size of an array inside a struct, like I'm doing down here, or the value on a case inside a switch statement. We're not really going to use this, but I thought it's worth seeing. It's kind of a weird secondary use of enumerated types as a way of getting a compile time constant value, probably one that they didn't have in mind when they designed the language. That was one of our two bigger topics for today. Enumerations as, one part of the C language that we hadn't seen until today. Questions before we talk about the next one? The next one is a union. And enumerated types, I said, well, these are kind of like what you have in Java. Unions, Java doesn't have anything like that. A union is like a struct in that it's a container for multiple fields. Now that's what I'm showing up at the top here. I've got a container, a struct, and it contains contact information. I'm pretending maybe you've got an email that's, room for a 24-character string. Maybe you've got a phone number and, maybe that's 3 little short numbers like the one I've listed here. Maybe you've got global GPS coordinates. That could be 2 doubles. So here I've got a struct and it's got 3 different fields in it. And if you think about what that struct is, sorry, let me try that again. How that struct is stored. When you make a struct, you're saying, I need all of these things, and the compiler stores them one after another in memory. So maybe with some additional padding, this struct would be stored like the picture shows. The first field, and then after that, the next field, the phone number, and then after that, the next field, the GPS coordinates. A union is almost the same syntax. So down at the bottom, I made a union that has the same 3 fields, but instead of being stored one after another in memory, they're all stored using the same memory. For a struct, you use that when you need multiple fields, and you potentially need to use all of those fields. A union is when you need different types of data, like here, you need an email, a phone, you need coordinates, but you only need one at a time. So I kind of avoided saying for a union, you need either an email or a phone number or global coordinates, but not all of them at once. So when you ask for a union, you're saying to the compiler, I want you to store these 3 things in memory, but I only need one of them at a time. And that kind of makes sense for the example I picked for contact information. Maybe you only need an email address, or you need a phone number, or maybe you need GPS coordinates to find someone, but you don't need all of that stuff. So a union would let you store any one of those things, but using the same memory. So using the same chunk of memory, you could store either an email address, or you could use that same memory to store these 3 shorts or these 2 doubles. That's what I'm trying to show in this picture. You can think of them as all occupying the same memory. So if you stored something in the phone number array, and then later you went back and stored something in the email array, you'd be overriding the memory where you just stored the phone number. So a union is, a struct is for when you got a bunch of fields and you need to be able to use them all. A union is when you need a bunch of fields of different types and you need to be able to use any one of them. So it's a way of building a thing where the stuff you need to store could vary from one instance to the next. And that's what I'm trying to show on my next slide. Questions before I try to talk through this example? All right, so for a union, the field you use depends on the instance. You get to pick. So up at the top, I'm pretending I've got the same union I defined down here, so contact info. Syntax is like a struct. So keyword union, name of the new union you want to make, and then a bunch of fields inside curly brackets, typically with a semicolon right after the closing curly bracket. It's just like a struct. If you wanted, you could start declaring variables right there. The semicolon says that you're done or you don't need to declare any variables, so that's why I put that there. So we're pretending we're using this union. I make, just like a struct, unless you do something with typedef. When you want to make an instance of that union, you have to use the union keyword. So that's what I did here. I want to make a contact info named Bill. Bill's got a phone number, so I fill in the 3 parts of Bill's phone number. Then I make another contact info Mary, but for Mary, I'm going to use the email address. The syntax for initializing is the same as struct. So if you want to initialize the email field, you could do it in a separate line or separate lines like I'm doing up here, or you could use initialization syntax. Here I'm saying go ahead and set Mary's email field to contain the string. If I do that, then I'm using the same memory as the phone number. So for Mary, if I'm storing an email address, I can't also store a phone number. That same memory is getting used for either of those. But for Bill, I'm using the phone number part. For Mary, I'm using the email part. When I access these, it's up to me, the programmer, to remember which thing I used. So down here, I remember, oh, for Bill, I stored a phone number. So I'm going to go get the 3 parts of Bill's phone number, and that'll work just fine. For Mary, I remember I stored an email address, so I can print that out as a string just fine. But if you mess it up, like for Mary, since you stored an email address, that overwrote the same memory where you could have stored a phone number. There's nothing to keep you from accessing the phone number field. It's just, it'll probably look like garbage, because here, when I look at the phone number array, the elements of this phone number array are really looking at the same memory that's storing the string. I'm just down here, I'm saying, oh, pretend that was holding 3 short values instead. And like I said, it's probably going to look like garbage if you do it like that. Why would you want to use unions? It's mostly about reducing the memory footprint of your program. If you had something like contact information, but you didn't need a phone number, email address, and GPS coordinates for everybody, you just needed any one of those, then a union would let you save memory. It lets you, with help from the compiler, it lets you build a representation that can store any one of those things, but not all of them, just any one of them. And I should have said this, I don't know if this was on my slide, but up here for a struct, sorry, it's going to use an amount of memory that's the sum of all of its fields, possibly with some padding. For a union, it's just going to need memory that's the largest of its fields, maybe also with some padding at the end. So just as an example, down here for email address, that's 25 bytes. For phone number, well, that's 3 shorts, so that's 6 bytes in size. Each of the doubles is 8 bytes in size, so an array of 2 doubles would be 16 bytes. So email address is the biggest field. My picture doesn't really look like that, but email address would determine the size of this union. It's got to be at least big enough to hold that 25 element array. And in practice, it would probably pad that up to probably up to 32 bytes in this, but I'm not sure I tried this example. Questions before I try to move on? All right, so I was trying to make the point, why would you use a union? Typically, you'd use it to save memory. So here we can make a contact struct that holds, you can read it off the slide, that holds a name of a person. I've got a field for that. And holds contact info down at the bottom. So I'm putting that union inside the contact struct. This part contains either email address, phone number, or GPS coordinates, but only one of them. So this part of the struct is where I'm saving some memory. I'm not having to store everything, just any one of those three things. Remember, it's up to the programmer to keep up with what they stored. So if I was going to make a list of contacts, and that's what I'm doing down at the bottom, I'm making an array of contacts, then maybe some of them have email address, maybe some of them have phone number, maybe some of them have GPS coordinates. So I better remember which of those fields is being used by each instance. And that's what this middle field is doing. In fact, that seems like a good job for an enumerated type. I might have some instances of contact where I use the email address. I might have others where I use the phone number. So for this middle field, I'll have a field name type, and it'll only have three possible values: email, phone, or coordinates. Those aren't the fields of the union. Those are just my names for the three values that type can have. If I store the email address, I'll set type to email. If I store the phone number, I'll set it to phone number or to phone, and so on. And that's what I'm doing down at the bottom. Let's pretend we're making an array of contact information. And we've just got an example for the first one. For Mary, we're going to store Mary. We put that first, so that's going to go in the name field. For the second field, well, we said email is going to go in the type field, and email is just the name of this first value in the enumeration. And then since we said we're going to store the email, or we're going to use the email field, we better make good on that. We better do what we said we were going to do. So here, this inside curly brackets, that's the initialization value for the contact info struct. And that's our union. I could have filled in any of its three fields, but only one of them. Here, since I said I'm going to store email address for Mary, that's the one I fill in. I think this next slide is just saying what I already said. That middle field, the type field, that's just something I added so that with each instance of contact, I can remember what part of the contact info I'm using. The compiler doesn't do that for me. It's up to me, the programmer, to remember which part of the union I'm using. So here's how you could build contact information. Here's the same code. I just threw away the stuff at the top to get a little bit of space back. And I added one extra contact just to have a better example. So now maybe our list of contacts has Mary, where I remember her phone number, and Bill, Mary, where I remember her email address, and Bill, where I remember his phone number. And then if I'm going to use this array of contact information, I'm going to need to keep checking the type field so I know which of the fields to use in the union. And that's what I'm doing down here. This is just a piece of pretend code that tries to loop over. It's just a code fragment that tries to loop over all the contacts. And for each one, I'm going to print out their contact information, but I have to check the type. So if for the ith person, I'm storing their phone number, I go get those three parts of the phone number and print that out. Otherwise, if for that person I'm storing their email address, and I didn't have room for this code, but I would print out the email, and something similar for GPS coordinates if I wanted that. Questions? I said this before, just like with struct, you can use typedef to give a short name for the union, so you don't have to say union every time. But really, I feel like you rarely end up doing this, because you rarely end up having a union that's just sitting outside any other type of object. When you have a union, it's almost always inside a struct. So this is showing typically how you would do what we were just doing. I've got this union. I called it info here, but I got this union. I didn't even really give its type a name. If I had, that would have gone right here after the word union. Or I could have used typedef and I could have put the name at the end. But I didn't do either of those things. I'm just making a field named info, and it has a union type, so it has these 3 fields, but I don't have any name for its type. And that's okay. I would say my plan is I'm never going to use this union anywhere except inside this struct. If I'm talking about an instance of the struct, I can still say .info, and that's talking about its info field. And since its info field is a union, I can say .info.email to get to the email part of the union, or .info.phone to get to the phone array in the union. I don't really need a name for that type if the only thing I'm going to do with that union is make this info field. So backing up a slide here, I was making the point that you can use typedef to give a short name for a union. But since unions almost always show up as part of a struct, often they don't even get names. They're just used to define fields of a struct. So you can have a struct that can behave, in this case, one of 3 ways. You can have some instances of contact where you're using the email field, other instances where you're using the phone field, other instances where you're using the global coordinates. I said when we started talking about this, Java doesn't have anything like this. And that makes sense. Unions are all about taking a chunk of memory and saying to the compiler, I want to be able to use the same piece of memory different ways. That's kind of what we've been doing in this example. I want enough memory to hold either an email address or a phone number or GPS coordinates. And I want to be able to freely pick which ones I want to use, which means, kind of like we saw in one of our early examples, you could save something in the .email field, and then if you tried to access it as .phone, you would be accessing the same memory as if it had a different type. And that can be awfully handy. We've done that a few times in this class. Maybe you've got something stored as an int and you want to look at each of the bytes in that int. This could give you an awfully convenient way of doing that syntactically. Java would never let you do this because Java, in fact, any language that's kind of strict in typing, it wants to have control over the type of a value. In Java, they came up with some awfully clever ideas to make sure that programs couldn't get around security measures by just changing the type of data. So if you write a piece of code in Java and you say, store this thing as an int, Java makes it so you can't go back later and say, you know, that thing I stored as an int, now I want to access it as if it's a reference to an object. They don't let you switch the type for something that's stored without actually doing a type conversion, and they'll reject type conversions that don't make any sense. Unions let us do this in C, but Java really wouldn't be able to do that without violating its type system. We can do something similar in Java. Unions in C are kind of used to make structs that behave like, you'll sometimes hear these called variant records. Structs where you can store one thing in it, or later you could store something else in it. So you could have structs where each one could be storing slightly different stuff. Java won't let you do that directly, but normally this is done through inheritance in Java. If you wanted a bunch of contact information for a bunch of different people, and for some of those people you needed email address, and for some of those people you needed phone number, you'd probably make a superclass that had their name. And then you'd make as many subclasses as you needed for the different types of additional information you wanted to store. So what used to be done with things like variant records in a language like C or Pascal, object-oriented languages tend to do that with inheritance. You can always make new subclasses, and those subclasses can add new fields that they want. We got 2 topics left, and they'll have to wait for next time, but they're really short. So we've just got 2 keywords, volatile and restrict, and you've probably seen these, especially restrict, if you've looked at the documentation, but we haven't officially talked about them yet, so I'll try to explain these quickly. But like I said, that'll have to wait for next time. You should be in good shape for your quizzes, your quiz and your exercises for this weekend. I'll double check to make sure that you are, but we're just about caught up, so I think you'll be okay on that. I'll hang around after class if people have questions. Otherwise, good luck finishing up your project, and I'll see you at the start of next week.
Quick question.
Hang on, I haven't stopped recording yet because I